one. You got two options. Which one? Where would you put the material to fix the plane? Okay. Yes.
I reinforced the black circles because it's the planes who didn't make it back, and that's most likely where they got shot and where they were destroyed.
Okay. So the military looked at this plane and said, we should put more material where the bullet holes are, because that's where they're getting shot. Let's protect the planes. The mathematician, hold on, I'll get you his name because they actually gave me his name. Abram Wald said we should protect the planes where the bullet holes weren't. He said that the planes that came back were not a random sample, because you only had the ones who survived. Okay. And based on that, he said that the bullet holes should have been a lot more random. They looked like they were very grouped in certain spots. All right. So he said that, well, the planes that didn't come back, the bullet holes were more random. They were probably hit in those spots where these planes didn't have bullet holes, which probably means that's why they went down. Luckily, the military actually sided with the mathematicians and reinforced those three areas and saved a lot more people. So, and if you think about it, these spots are like this spot here. These are your gas tanks where the fuel goes to the actual engines. And this is your fuselage in the middle. So if you cut up that part, it's going to weaken the plane and it'll fall apart. So also kill the people that were back here. So that's why those bullet holes or the concept came up. So we had a concept of what's known as a random sample. What's a random sample? We talked about this before. Yeah.
Is the random part the group the sample falls into, or what values are within? Like, are they having like a randomly shared trait, or?
So how? I guess. Okay. Let me reword the question, because I got what you're thinking. So, how would you choose a random sample? So we said in this plane, all the planes that came back, that wouldn't be considered a random sample. Because why would that not be a random sample? It's only the survivors. So not all the planes survived, right? So that'd be like choosing all the people in this classroom and saying, I chose a random sample of the school because you randomly picked this class. Okay? And that would change things. Like, it's not necessarily everybody's going to choose this class or have to take this class. So random samples means you have to choose from everything, and it's got to be somehow created or somehow picked randomly. And there's a lot of different ways we're going to do that. We'll talk about more of those on Wednesday. But the biggest thing is the sample cannot be biased. So a biased sample is one that overrepresents or underrepresents some segment of the population. So in the case of the plane, it was biased because it overrepresented the ones who survived. Next term we're going to use is called a sampling frame. This is the list of which identifies all members of the population. So to create a random sample, we have to know what the population is to choose from. So in the plane situation, we're looking at how to protect the planes. This population is going to be all the planes, at least of that type of plane.
Does it have to be a finite population?
Mm,
Or just because it references it there? Is that a requirement or no?
can you give me an example of an infinite population? She's like, I didn't want to ask that question. Yes.
If it's unknown.
Is it still finite? So that's the question. So it's like, so yes, and the next thing it says a finite population. In mathematics, we have things that are known as we have infinities. However, can you have an infinite population of something? You can have an insanely large population of something. Like if we were going to say all the grains of sand in the world, that's an insanely large number. But is it infinite?
Making it hard to count doesn't make it.
Correct. That's the difference. Right. So just because it's not a small number or something that I can easily list doesn't mean it's fine, not finite. So like even the population of the world, we're at like what 9 billion people. That's a huge number. Still not infinite. So most thing, well, pretty much everything you deal with in statistics is dealing with a population. So that's going to be a finite type of population in that respect, in terms of math terms. A sentinel random sample is where every possible sample has the same size, has the same probability of being selected. So that means if I have 30 people in here, you all have a 1 in 30 chance of being selected. That's random. Okay. There is no, I like this side better because you're on this side. Or so me picking people who answer questions is not random because only a few people are actually answering questions. I'd love more. All right. Where's my? Oh, I'll put that one afterwards. Okay. Students in a marketing class have been asked to conduct a survey to determine whether or not there's demand for an insurance program at a local college. Students decide to randomly select students from a local college and mail them a questionnaire regarding the insurance program. Of the 150 surveys that were mailed, 50 students responded to the following survey. Pick the category that best describes your interest in an insurance program. 50 people said very interested, 15 somewhat, 10 interested, 5 not interested, and 20 not interested at all. All right. So, was this a random survey? Or is this did we get a random sample and is this a valid survey? Somebody other than the two that always answer me. Yes.
I would say yes, because in the thing, it says that the students decide to randomly select students, so it's like a. That makes sense.
Okay. So they randomly selected the 150 surveys they mailed out. Okay. So are they the responses on all 150 surveys? No, it's only on the 50 that came back, right? All right. I think I've asked this question before, but how many of you, if you got a phone call asking you to, or that you didn't know, would you answer the phone to begin with? Okay. How many of you get mail at your house? All right. How many of you basically look through for anything important and throw all the rest away? So if you got this survey, what would the survey happen? What would the survey be done? It'd be in the trash. Why?
Because unless I care about it, I'm not gonna answer it.
You didn't even open it.
Yeah.
How do you know if you cared about it?
I might open it. Yeah, but I probably.
Okay, so at least, so you might even at least open the junk mail. Okay.
I usually check if it is something important, but.
Nielsen, anybody know who Nielsen is? So Nielsen's a company who does all your TV programs. So they used to actually send out surveys with money in them. $1, $5, $10 bills, like literal cash, like not even like a check. actual cash in the envelope. I wonder how many of those literally just went right in the trash. All right, so nobody in here would have filled out the survey. So is it random? Who's filling out the survey? If you look at it, 65% of the people that mailed it back were interested. Okay, but only a third of the people actually filled out the survey. So it's 65% of 30% or 33%, right? That were interested in it. So if you assume that the other 100% of the people, or 100 people weren't interested because they threw it away and didn't answer it, gives you a lot different survey results, right? So would these survey results be a good representation of the student body? Okay. So totally like not what this was originally the question was about, but it actually, the numbers come out to be almost the exact same. Who won the last election? Who won the last presidential election? Even if you don't like him, who won? Okay. What percentage of the vote did he get? Okay, so it was almost 50%. It wasn't quite 50%. If I asked an entire group of Trump supporters, it would have been at least 50%. Or at least they would have said 50% because they wanted exactly that number. All right, so he got about 49 point, I think it was like 8 or something like that. I think Harris got 47.4 or something like that. It was that about a number, and then there was like 3% was for the Green Party and Libertarian Party and some other people that were running. Okay, so 36% of the population didn't vote. So in actuality, only 31% of the people voted for Trump. Not even a third. Okay. Same concept as this. It's actually exactly the same as this. You had 2/3 of the population in this respect choose to either not vote because they didn't care in this situation, or actually, if you look at the other 25% of the people who actually sent it back, so another 13 people, so 113 people really aren't interested in this because they either sent it back and said they're not interested or didn't even care enough to respond. Okay, so you can start to see how that pieces, when it's not randomized, can get you different types of results. Polling is actually more randomized when they do polling concepts. However, there's a lot of other issues that go along with polling and why that's not very accurate either. But elections are not random samples either. So, all right. There's an interesting concept here. So it's known as a sampling distribution of a statistic. So instead of just taking one individuals and looking at them, if I took a sample of all of the different surveys that were sent out, I could get a better estimation of what's going on. So, for example, if I did a random survey at the school asking, what's your favorite type of car? Or actually, let me not do that. Let me actually come up with one that's going to give me a number. What's your income? That could give me a number. Okay, so what's your income? So I do a survey, I get the data, and I have every single one of you in here do the exact same survey. So you're going to randomly ask 100 people what their income is. All right. Are we all going to get the exact same average or mean? No, it's going to be a variance, right? Now, if I took all of our surveys and averaged the averages, that number probably be a lot closer to what the actual average was for the entire population. Does that make sense? So if we take it, we actually look at groups of data instead of just individuals. We're going to get a lot better understanding of what the data is going to give me. Okay. So that's where that sampling distribution statistic, we're going to look at like sample mean or sample proportion are the two that we're going to look at a lot. So we're going to take it when all the population, possible sizes of that sample are taken, and then we look at that. The point estimator is that single value that we get from it. And that's typically very close to the actual true population value. We then can do everything we did before, looking at the z-table and stuff like that. It actually gives me a nice curve. It's actually the same concept we were doing before. The average value of estimators equals the population parameter being estimated. The estimator is considered to be unbiased. So if they're the exact same, then it would be an unbiased representation. Everything comes in as biased. And in all honesty, if I ask every single person in here to randomly do a survey for me, even while you're doing it, you have biases on who you're going to talk to and everything else. You're not just going to randomly walk up to people and talk to them. You're going to talk to people you're comfortable talking to. So your survey results are going to be biased to begin with. So you get that information. All right. These two targets up here are unbiased. These two targets are biased. All being close to the value you want does not mean they're less biased. Okay. So this is more scattered, but if you look at it, it's scattered pretty evenly. And if you took all the distances to the center, it's probably going to end up being averaging up to be close to the center, just like this one is. Where these two, if you looked at them, the averages are skewed. They're not at the center. So those are biased results. If you're a shooter, either one of these actually would be better than this one because you want tight groupings, but not when you're looking at statistics. There are three unbiased estimators. These are the three we're going to be dealing with. The first two we're going to be dealing with. This last one we are not, but it actually does exist. The sample mean is an unbiased estimator of the mean, and the sample proportion is an unbiased estimator of the proportion. So we've dealt with those before. We've dealt with the X bar and the P hat, remember? We've done both of those. All right, the central limit theorem. So, if a sufficiently large sample, heard me say this number before, 30 people, is drawn from a population with a mean and standard deviation, the distribution of the sample mean will have the following characteristics. That means that I only really need to truly ask 30 people to be able to do this. I don't need thousands. I don't need millions. I need 30 people. The more people you ask, the better data you're going to get. And the closer to that mean you're going to get. But 30 is all you need. It will be a normal distribution, regardless of the distributions of the underlying population. So that the 30 people you pick, you will get a normal distribution out of it. The mean of the sample means equals the population mean. So when I take the mean of all those surveys that I did, it's going to be equal to the mean of the actual population. And the standard deviation of the sample mean equals the standard deviation divided by the square root of the sample size. So this one's kind of easy. Whatever you get for this is going to be that. But this is a formula you're going to have to use. I'll get rid of that circle so you can finish writing. So as my sample size gets bigger, my curve gets smaller. Because I'm basically dividing by a bigger number down the bottom. So it's going to get smaller and smaller. Which means more of the data is compressed into a closer area, which gives you a better representation. All right, let's do one. So my mean is 30. What's my standard deviation? Because those are the two pieces I need. Does it give you your standard deviation? Gives me by what? Variance. And variance is, how do I find standard deviation from variance? Take the square root of it. So what's the square root of 25? It's 5. Use your calculator. It's a little check mark symbol. And unlike most of your other math classes, it's just 5. It's not plus or minus 5. And what's my n? What's my sample size? 100. Okay. So they want to know the probability that x r is going to be larger than 31. That's what they're looking for. All right, so if I didn't have the n, how would I do this problem?
Did you solve for it exactly? Like the other problems in the last section?
Well, how would I figure out the problem? So we're not going to go necessarily backwards because I have 31. We want to actually go forward. I want is exactly what we did before.
Just find out.
We're looking for the probability. We're looking for that number. So we're going to use that z table. So how would I do it? What do I need to do first? Yes. Find z. So what's the formula for z? Yeah. Yes, all these are normally distributed as long as I have a sample size greater than 30. That's that key of that central limit there. Well, as long as my sample size is greater than 30, it's normally distributed. So what's my formula for z? This was your test. Okay. So the only thing that changes, because we have our n, is you're going to divide by the square root of n. Because remember, I want that sample standard deviation. That's the piece that I'm looking for. So I'm going to have the square root divided, the standard deviation divided by the square root of n on the bottom. Everything else stays the same. So in this case, I have 31 minus 30 divided by 5, square root of 100. So you can do this a couple different ways on Desmos. I always hit my division sign first, so this way I don't have to worry about it. And then I would do it down here. So 5 divided by square root of 100. So square root of 100 is easy. It's 10. That one you should probably know. It comes out to be a whole number. The vast majority of your square roots are not going to come out to be a whole number. So don't find that number first and then round. Use the square root of the number. Because if you do that, things will change. All right. Especially when you're dividing that number can get quite small when you're doing those calculations. All right. So my z in this case is 2. All right. So take out your z tables. Still going to need them. Still going to use them. Don't lose them. I'll eventually give you another one, but or a different one. But right now, this is the one we're using. So we're looking at 2.00. So what is my number on the z table? What do I get? Yep.
0.9772.
All right. Is that my answer? Because I want greater than. So it's the complement to that. So I got to subtract that from 1. So I get 0.0228. And that's my answer. All right, what if I took this problem and instead of doing 100, we did 1,000. What's going to change? Is this number going to get bigger or smaller? So that number right there, is the answer going to get bigger or smaller?
Bigger because the curve flat.
Okay. Everybody agree with them? Okay.
Because you're dividing the square root by n, and it's the square root of 1,000 is 31 as opposed to.
Okay. So my number now about okay.
By a bigger number, right?
So let's see what happens. So we're still going to the 31 minus the 30 over 5 divided by the square root of 1,000. So my formula is going to change here. I'm changing the 100 to 1,000. And I get 6.332. So what's the probability that my sample mean will be larger than 31?
Very minuscule, so it's not even on the table anymore.
Just make up a bunch of zeros and put a 1 at the end, basically. Yeah, basically it's not going to happen. All right. So the more I survey, the chances of it being that far out, it's almost nothing. Okay. So in the first situation, there was a 5% chance, or actually 2.2% chance, 2.3, that it would be larger than 31. If I did 1,000, the chances of it being larger than 31 is basically nothing. It's basically never going to happen. So we have a lot better area in there, or a lot closer representation to what the actual information is going to be. And that's really where your sample sizes come into play, right? The more people you ask, the better your data is going to be. Okay.
So if that happened on like one of our Hawk problems, would that mean, like, would we put our answer as 0.0000?
I don't think they're ever going to give you one
Okay.
that's far out, because it's depends on what you put. They might actually have a box if it was there that says basically 0 or approximately 0. So, all right. So if you buy 2 bags of sugar, let's say at 1 or 5 pounds each, are they going to be exactly 5 pounds if you weighed them? Yes.
Probably not.
Okay. They're not all going to be exact, right? We're always going to have that little bit of a variance. So is it okay for it to be a little less than 5 pounds? Yeah.
I think in the mind, no.
All right, but how much less would it have to be before you complain? Or how much less would it have to be before you even noticed?
That's a real
That's a
question.
good question.
Okay, so, and that's the thing, it's like how much less until you actually notice the difference and would actually complain?
I guess if it was like something like, for example, fertilizer, I wouldn't really notice because it's all like many grains. But if, for example, like it was, I don't know, a package of fries, like you could see the difference a little easier because it's a smaller.
Okay, if you're missing 2 or 3 fries, you're gonna notice.
Maybe, I don't know.
Do you ever count your fries? Do you ever go home and actually weigh the bag you buy? No, nobody does, right? So unless it's drastically different, you're probably not going to notice. The one thing that everybody seems to notice, and it's actually accurate, is a bag of chips,
Yeah.
because 2/3 of the bag is basically air. However, the weight in the bag is correct, or very close. Okay, they do it because it actually prevents the chips from breaking. That's literally why they do it that way. If it was full, the chips would all shatter and ship it. So that's the thing. It's like, how much would it be till you actually noticed? You're never going to be able to inspect everything. However, there's things called weights and means. So, like if you ever go to the gas station and look at their stickers on the gas pumps that say the last time they were checked, because when you're pumping gas into your car, you want to make sure you actually get a gallon of gas. So they actually go and they check the gas pumps. Do they check it all the time? No, they do a couple tests. As long as it comes out to be exact right, you're good. Or within a margin of error, you're good. However, gas expands and contracts. So if you get your gas in the morning, it actually is, you're going to get more gas than if you get your gas in the heat of the day, because the gas expands. So that's that margin of error that you're going to have. So when we're looking at that, they use statistics to determine what is an acceptable difference. And they have a certain percentage or value. So let's look at this one. Fertilizer company fills bags for retail sale. Bags of normal fertilizer have a distributed mean weight of 15 pounds and a standard deviation of 1.7 pounds. What's the probability that a randomly selected bag of fertilizer, just one, will be between 14 and 16 pounds? This is exactly what you did in your test. How would I do it? So I'm going to erase this because we're going to do this question next on the next page. What's the standard or the mean? Okay. What's the standard deviation? Okay. And I'm looking for, sorry, my means there. So I'm looking for the probability of between 14 and 16 pounds, right? So I have X is 14 and X is 16. I need to find them both. All right, so find me the Z for 14 and 16. All right, so what's the Z? Yeah. Okay, and what do you got? 0.59? Okay, so this one's negative. What'd you get for the 16? Gonna be the exact same thing because it's still 1 on the top, right? Okay, so now we need to look up those values in the z table. And what's the negative one? And what's the positive one? Okay. What am I going to do with those two? Let's subtract them. They're both coming from the left, right? So if we looked at my little curve, I'm looking between them. So I want to take off this part down here from the big part. So I'm going to subtract those two. So that gives me what? Yeah. All right. So the probability that a randomly selected bag of fertilizer will weigh between 14 and 16 pounds is less than 50%. Okay. Yes.
Is that good or bad?
You have a less than 50% chance of getting a bag that's within 1 pound. Now, the question is that that's going to be positive or negative. So you could end up working out of the other end and being good. However, if we just look at less than 14, that's still a 20.22776, right? So there's still a 27% chance that you're going to get less than 14 pounds. There's a 27% chance you're going to get higher than 16 pounds too. Okay. So if I'm an inspector and I want to check the company, make sure that they're doing right by their consumers, am I just going to pick up one bag and check it? No, because it's just one. Like I'd have to do that a bunch of times, right? I'd have to do that and see the sample sizes. So let's do the same problem, but this time we're going to look at 35 bags. So instead of just looking at one bag, I'm going to look at 35 bags. The process that we're doing is everything is the same except for one step. That one step is where I find my z. So my mean is still 15. My standard deviation is still 1.7. My n in this case is 35, and I'm still looking for the probability between 14 and 16 pounds. So the z for 14 and for 16. So I'm still going to do 14 minus 15 divided by 1.70, except for this time, I'm going to do the square root of 35 again. That's the piece of ignorance. Now, the top number is not going to change except for a positive or negative. So you do not have to do both of them. Just realize one will be negative, one will be positive. The z will still be the exact same number, though. All right. So now if we look at our z table for 3.48, we get 0.9997 and 0.0003, right? All right. So again, I would subtract those two, right? So the chances of a pallet of 35 fertilizer bags having an average weight of less than 14 or greater than 16 would be 0.9994. So I could weigh the pallets of the 35 bags, which is a lot more efficient. And as long as they're between the 14 and the 16 pounds, it's good to go. So as long as that average is there, it's good to go. So that's how they start to look at sample sizes and being able to look at a group of things instead of just one individual thing to check and make sure things actually work out correctly for us. So, and they do this for all the things, like your boxes of cereal and everything else like that. They have to, when they go through the machines, they check cases of them to make sure that the weights are correct to determine if their machine is working correctly and it's calibrated correctly. So while we think that going less is in their best interest, it's never in their best interest to have their machines working improperly. So if it's always filling things up that are less, then that's a problem, just as if it's always filling up the things higher. So in either one of those cases could be true. So they want to make sure they're working effectively. All right. Do A, B, and C.
Well, like, have it written out with letters instead of numbers like this. Like it says 45.
Oh, it's possible. That's possible.
Okay.
This is from their book, so that's possible. Yes, don't always just look for numbers. Oh, was it greater than? Less. So we got negative 1.84. 1.84 is 0.0329. That's what you should have gotten for the first one. And since it was less than, we don't have to subtract from 1. What was it? Where was the number? 2.35. So this one was greater than 17. So 2.35. And do we have to do is it the number we get or are we subtracting it from 1? We're going to find the complement of it. So the complement to that is 0.0094. Yes.
I got this. I'm going for the last one, but I'm not sure what to do now.
I'm going to put them up there in a second. You'll never see me write 100, but it's basically 100.
My answer would say 51.
Actually, I should put the decimal point in front. So, because again, you'll never have exactly 100, and you'll never have exactly 0, because those are two very specific things in statistics. Because 0 means it's never going to happen, 100% means it always is going to happen. There's always a chance of it being outside of that. But it is so extremely small. That's why it's basically 100 or put a whole bunch of 9s. So, because neither one of those numbers is on our table, so it's going to be well past what those numbers are going to be there anyway. So, this is where we can start to use those means to actually help us get a better understanding of what's going on. Yes.
You just may know it was practically 100%. If we can't see it on. April.
Because we're going between them.
Oh, right.
So if it was outside, if it was less than 113 or greater than 18, then it would be 0. So yeah, if we're looking at the curve, we're looking at a number that's down here and up there, and we want the number in the middle. So it's basically everything. That's how we can determine that. So. All right. Any questions with it? That I just did it. Okay. So as you can see, not much has changed from what we did before. Just that little change in the formula. Pretty much everything else is exactly what we've been doing. So most of the situations that we're going to be doing going forward are like that. It's just a little change in the formula, but the concept, the overarching theme with the Z table and stuff like that is going to be the same. So that's why I said those Z tables are going to become your best friends. You're going to use them constantly. All right. I will see you on Wednesday.